In 1977, humanity launched its most ambitious message in a bottle. Two spacecraft, Voyager 1 and Voyager 2, left Earth on a journey that would take them past Jupiter, past Saturn, past Uranus and Neptune, and eventually out of our solar system entirely. They carried golden records containing the sounds and images of Earth, greetings in 55 languages, and music ranging from Beethoven to Chuck Berry. Let me tell you the full story of how these missions came to be, because it helps us understand both their achievements and their limitations. In the late 1960s, NASA aerospace engineer Gary Flandreau discovered something remarkable. In the late 1970s, Jupiter, Saturn, Uranus and Neptune would align in a configuration that occurs only once every 175 years. A spacecraft launched at the right time could use gravitational assists to visit all four outer planets in a single mission. This was called the Grand Tour, and it was an opportunity that wouldn't come again until the 2015s. NASA initially planned an ambitious Grand Tour program with 4 spacecraft, but budget cuts in the early 1970s forced them to scale back. Instead of 4 Grand Tour spacecraft, they would launch 2 simpler Mariner Jupiter-Saturn probes. These probes were eventually renamed Voyager 1 and Voyager 2. Voyager 2 launched first on August 20th, 1977. Voyager 1 launched 16 days later on September 5th, 1977. Despite launching second, Voyager 1 was on a faster trajectory and would reach Jupiter and Saturn before its twin. Both spacecraft carried identical scientific instruments: cameras, spectrometers, magnetometers, and plasma detectors. And both carried the famous golden records: 12-inch gold-plated copper discs containing sounds and images representing Earth and its inhabitants. The contents of the golden records were selected by a committee chaired by astronomer Carl Sagan. They included greetings in 55 languages from ancient Akkadian to modern Wu Chinese, sounds of Earth, wind, rain, surf, thunder, birds, whales, and various human activities. 90 minutes of music from around the world, including works by Bach, Beethoven, Mozart, and traditional music from many cultures. 115 images encoded in analog form, showing scientific concepts, human anatomy, and scenes from Earth. Recorded greetings from US President Jimmy Carter and UN Secretary General Kurt Waldheim. Each record came with a cartridge and a stylus, and the cover included instructions for playing the record, written in symbolic language that, theoretically, an intelligent alien could decipher. Carl Sagan described the golden records as a bottle cast into the cosmic ocean. It was an optimistic gesture, an assumption that the universe contained minds capable of finding and understanding our message. But the universe had other plans. It was humanity's first attempt to reach the stars, our declaration that we existed, our hope that someday, somewhere, someone might find these tiny machines and know that a species called humans once lived on a pale blue dot orbiting an ordinary star. That was 48 years ago. And in those 48 years, Voyager 1, the fastest and most distant human-made object in existence, has traveled approximately 24 billion kilometers. That sounds impressive. It sounds like we're making progress. It sounds like the stars might actually be within reach. But here's the thing that nobody talks about. Here's the truth that space agencies don't put in their press releases. Here's the mathematical reality that proves, beyond any reasonable doubt, that humans will almost certainly never leave the solar system. Voyager 1 has been traveling for nearly half a century at speeds of over 60,000 kilometers per hour. It's the fastest object humanity has ever created. And at its current speed, it would take approximately 73,000 years to reach the nearest star. 73,000 years. To put that in perspective, 73,000 years ago, Homo sapiens were just beginning to migrate out of Africa. We hadn't invented agriculture. We hadn't built cities. We hadn't developed writing. The entirety of recorded human history, every empire, every war, every discovery, every person who has ever lived and died, fits within the last 5,000 years. And Voyager would need 73,000 years just to reach the closest star. Not to explore the galaxy, not to find habitable worlds, just to reach the nearest neighboring star system. The universe is not built for us. The distances are not human-scaled. And the Voyager missions, far from proving that we can reach the stars, have actually demonstrated the opposite. They've proven that we can't. Before I explain why, let me tell you what the Voyagers actually accomplished. Because their achievements are genuinely remarkable, which makes their failure to reach the stars all the more poignant. Voyager 1 reached Jupiter in March 1979, passing within 350,000 kilometers of the planet's cloud tops. It discovered that Jupiter's moon Io has active volcanoes, the first volcanic activity ever observed anywhere other than Earth. It photographed Jupiter's Great Red Spot in unprecedented detail. It discovered 2 new moons, Thebe and Metis. 4 months later, Voyager 2 arrived at Jupiter. It took more detailed images of the Galilean moons and discovered a 14th moon, Adrastea. In November 1980, Voyager 1 reached Saturn. It made the first detailed studies of Saturn's rings, revealing that they consisted of thousands of individual ringlets. It flew close to Titan, Saturn's largest moon, and discovered that Titan has a thick, nitrogen-rich atmosphere, the only moon in the solar system with a substantial atmosphere. The close flyby of Titan altered Voyager 1's trajectory, sending it out of the plane of the solar system. This meant Voyager 1 would not visit Uranus or Neptune, but it also put the spacecraft on a faster path toward interstellar space. Voyager 2, meanwhile, continued on the Grand Tour. It reached Saturn in August 1981, then pressed on to Uranus, January 1986, and Neptune, August 1989. It remains the only spacecraft ever to visit these ice giants. At Uranus, Voyager 2 discovered 10 new moons and 2 new rings. At Neptune, it discovered 6 new moons and the planet's ring system. It photographed Neptune's Great Dark Spot, a storm system similar to Jupiter's Great Red Spot. The discoveries made by the Voyagers revolutionized our understanding of the outer solar system. They found active geology on worlds we had assumed were dead. They discovered complex ring systems and diverse moons. They revealed that the outer solar system was far more interesting than anyone had imagined. And then, having completed their primary missions, they kept going. In 1990, at Carl Sagan's request, Voyager 1 turned its camera backward and took a series of images of the solar system from the outside. One of these images showed Earth as a tiny, pale blue dot, barely visible against the darkness of space. Sagan famously wrote about this image. "Look again at that dot. That's here. That's home. That's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives." He continued, The Earth is a very small stage in a vast cosmic arena. Think of the rivers of blood spilled by all those generals and emperors so that, in glory and triumph, they could become the momentary masters of a fraction of a dot. Think of the endless cruelties visited by the inhabitants of one corner of this pixel on the scarcely distinguishable inhabitants of some other corner, how frequent their misunderstandings, how eager they are to kill one another, how fervent their hatreds. Sagan was a visionary. He believed that humanity's future lay among the stars. He dreamed of generation ships and interstellar colonies. He imagined a future where humans spread across the galaxy, carrying life and consciousness to sterile worlds. But Sagan also understood the alternative. In the same passage he wrote, "Our planet is a lonely speck in the great enveloping cosmic dark. In our obscurity, in all this vastness, there is no hint that help will come from elsewhere to save us from ourselves." That's the double-edged truth of the pale blue dot. Yes, we're small. Yes, we're alone. But also, this is all we have. This tiny world, orbiting this ordinary star, is the only place we know of where life exists. Sagan believed we could transcend our limitations. He saw space exploration as the path to survival and enlightenment. But what if the limitations are absolute? What if the cosmic dark is truly enveloping and we can never escape it? Then the pale blue dot isn't just our home, it's our prison. A beautiful prison, full of wonders, sustaining billions of lives, but a prison nonetheless. This isn't the message Sagan wanted to convey, but it might be the message the universe is sending. It was a humbling reminder of our small place in the cosmos, and it was taken from just 6 billion kilometers away, barely outside Neptune's orbit. In 2012, Voyager 1 became the first human-made object to enter interstellar space, crossing the heliopause, the boundary where the sun's influence gives way to the interstellar medium. In 2018, Voyager 2 followed, crossing into interstellar space at a different location. Both spacecraft are still operating, still sending back data about the environment of interstellar space. Their nuclear power sources are slowly dying, but they have enough power to continue transmitting until about 2025. After that, they'll go silent. But they'll keep traveling. Forever. This is the story of why interstellar travel is almost certainly impossible for biological humans. Not just difficult, not just expensive, not just technologically challenging, impossible. And I'm going to show you exactly why. Let's start with the basics. Let's talk about just how far away things actually are. The nearest star to our Sun is Proxima Centauri, part of the Alpha Centauri system. It's located approximately 4.24 light-years from Earth. A light-year is the distance that light travels in 1 year. Light moves at approximately 300,000 kilometers per second, the fastest speed possible in our universe according to the laws of physics. Nothing with mass can ever reach or exceed this speed. In 1 year, light travels about 9.46 trillion kilometers. Proxima Centauri is 4.24 times that distance away. That's roughly 40 trillion kilometers. 40 trillion kilometers. Let me try to make this number feel real, because numbers this large just become noise. If you could drive a car to Proxima Centauri at highway speeds, say 100 kilometers per hour, non-stop, no brakes, the journey would take approximately 45 million years. If you could fly a commercial airplane at 900 kilometers per hour, it would take about 5 million years. If you could travel at the speed of a bullet, around 1,500 kilometers per hour, it would still take 3 million years. Even at Voyager 1's speed of 61,000 kilometers per hour, faster than any human has ever traveled, faster than any spacecraft currently in operation, the journey would take 73,000 years. These aren't engineering challenges. These aren't problems we can solve with better technology. These are fundamental facts about the scale of the universe. Space is big. Really, really big. So big that the distances involved are essentially infinite from a human perspective. But wait, you might say, Voyager is old technology. It was built in the 1970s with computers less powerful than a modern calculator. Surely we can do better now. Surely with modern technology, we could build something faster. Yes, we could, and it wouldn't matter. Let me show you why. The fastest spacecraft ever built is the Parker Solar Probe, launched in 2018. At its closest approach to the Sun, it reaches speeds of approximately 700,000 kilometers per hour. That's about 11 times faster than Voyager. At that speed, the absolute maximum we've ever achieved with any spacecraft, the journey to Proxima Centauri would take approximately 6,500 years. Still far beyond any human lifespan. Still far beyond any human civilization's lifespan. Still utterly, completely impractical. But let's go further. Let's imagine we could build a spacecraft that travels at 1% of the speed of light. That's 3,000 kilometers per second. That's 10.8 million kilometers per hour. That's about 15 times faster than the Parker Solar Probe at maximum velocity. At 1% of light speed, the journey to Proxima Centauri would take 424 years. Still multiple human lifetimes. Still requiring a generation ship or suspended animation technology we don't have. What about 10% of light speed? That's 30,000 kilometers per second. That's 108 million kilometers per hour. That's technology so far beyond our current capabilities that it borders on science fiction. At 10% of light speed, the journey would take 42 years. Finally, we're approaching a single human lifespan. An astronaut who left Earth at age 20 might arrive at age 62, old but still alive. But let me introduce another complication: relativistic effects. At 10% of light speed, the effects of special relativity start to become noticeable. Time dilation means that time passes slightly slower for the moving spacecraft than for observers on Earth. The formula is T-ship equals T-Earth times the square root of 1 minus v squared over c squared. At 10% of light speed, v equals 0.1 c. This works out to T_ship equals T_Earth times the square root of 1 minus 0.01 equals T_Earth times 0.995. So time on the ship passes at 99.5% the rate of time on Earth. Over a 42-year journey, Earth time, the ship would experience about 41.8 years. That's not a big difference, but at higher velocities, the effect becomes dramatic. At 50% of light speed, time dilation gives a factor of 0.866. A journey that takes 8.5 years in Earth time would feel like 7.4 years on the ship. At 90% of light speed, the factor is 0.436. A journey of 4.7 years, Earth time, would feel like only 2 years on the ship. At 99% of light speed, the factor is 0.141. A journey of 4.3 years, Earth time, would feel like only 7 months on the ship. This seems like it might help. If we could travel fast enough, time dilation would shorten the subjective journey time. But there's a catch. You still have to accelerate to those velocities, and the energy required increases asymptotically as you approach the speed of light. The relativistic kinetic energy formula is E equals mc squared times, open parenthesis, 1 over the square root of, open parenthesis, 1 minus v squared over c squared, close parenthesis, minus 1, close parenthesis. At 10% of light speed, the kinetic energy is about 0.5% of the rest mass energy. At 50% of light speed, it's about 15%. At 90% of light speed, it's about 130%, more energy than the total rest mass of the spacecraft. At 99% of light speed, it's about 600% of the rest mass energy. And you need this much energy just to accelerate. You'd need the same amount again to decelerate. The physics is unforgiving. Yes, time dilation could shorten the journey, but the energy required to take advantage of it is beyond anything we can imagine producing. Let me discuss some proposed solutions that haven't made the list, ideas that sound promising but fall apart under scrutiny. Cryogenic freezing. Put the crew into suspended animation for the journey, wake them up on arrival. This is a popular science fiction trope, but we can't actually do it. Current cryogenic preservation techniques kill the subject. We can vitrify, not freeze, tissues to preserve structure, but the process isn't reversible. No one has ever been thawed from cryogenic preservation and survived. Even if we could freeze and thaw humans, there are problems. Ice crystals damage cells. Metabolic processes don't simply stop, they have to be carefully managed. And we'd need to maintain the cryogenic systems for decades without failure. Cryogenic sleep isn't technology we're close to developing. It's not on any reasonable roadmap. Embryo colonization. Send frozen embryos and robotic systems to raise them at the destination. This avoids the need to keep adult humans alive for decades. Embryos are easier to preserve than adults. Robotic systems could theoretically grow embryos to fetuses, then to babies, then raise children to adulthood. But think about what we're proposing. Children raised by robots, with no parents, no human contact during their formative years. The psychological effects would be devastating. We'd be creating a population of feral humans, traumatized from birth. And what happens when they grow up? They'd have no skills, no culture, no knowledge of their origins, except what the robots could teach. They'd be colonists in name only, lost children on an alien world. This isn't colonization, it's abandonment. Slow ships. If we can't go fast, go slow. Take 10,000 years to reach the nearest star. Some proposals suggest using very slow propulsion, perhaps solar sails or ion drives, to gradually accelerate a ship over thousands of years. The energy requirements are lower, and there's no need for breakthrough technology. But who maintains the ship for 10,000 years? Mechanical systems fail. Electronics degrade. Software becomes obsolete. A ship that must operate autonomously for 10,000 years would need to be self-repairing to a degree we can't currently achieve. And the crew, whether biological or digital, would have to survive for 400 generations. That's longer than recorded human history. Languages would evolve beyond recognition. Cultures would transform entirely. The people who arrive would have no meaningful connection to the people who left. Slow ships stretch the concept of mission continuity beyond any reasonable definition. Space arcs. Hollowed-out asteroids converted into giant generation ships. This addresses the problem of building a large enough ship. Asteroids provide shielding against radiation and micrometeors. The mass is already in space, reducing launch costs. But hollowing out an asteroid and making it habitable would be an enormous engineering project, far beyond anything we've attempted. And you still have all the problems of generation ships. Multi-century transit times, energy requirements, the ethics of trapped populations. Space arcs are a bigger version of an unworkable idea. Size doesn't solve the fundamental problems. Beamed power. Instead of carrying fuel, receive energy from lasers based in the solar system. This is the basis of the breakthrough Starshot proposal. A powerful laser array accelerates small probes to high velocity. But beamed power has a range limit. The beam spreads out over distance. Eventually, the spacecraft can no longer capture enough energy to accelerate. For the Starshot probes, this isn't a problem. They're so small and light that a brief acceleration burst is sufficient. But for a crewed spacecraft, you'd need much more energy delivered over a much longer distance. The physics becomes impractical. And you can only accelerate. You can't decelerate using beamed power from the solar system. The beam would have to come from the destination, which doesn't have a laser array. Each of these proposals solves one problem while creating others. None of them offer a realistic path to interstellar colonization. But here's the problem. We have absolutely no idea how to accelerate a spacecraft to 10% of light speed. None. Zero. It's not just difficult. We don't even have theoretical propulsion systems that could achieve this for any reasonably sized spacecraft. Let me explain why. The fundamental problem with space travel is the tyranny of the rocket equation. Every spacecraft needs fuel to accelerate, but fuel has mass. An accelerating mass requires more fuel, which adds more mass, which requires more fuel. This creates a vicious cycle where the faster you want to go, the exponentially more fuel you need. And at some point, no amount of fuel is enough. For chemical rockets, the kind we use today, the maximum achievable velocity is limited to about 15 to 20 kilometers per second. That's fast by terrestrial standards, but it's only about 0.005% of light speed. At 0.005% of light speed, the journey to Proxima Centauri would take approximately 85,000 years, worse than Voyager. Because Voyager used gravitational assists from Jupiter and Saturn to boost its speed, a trick that's not available for interstellar travel. Okay, so chemical rockets won't work. What about nuclear propulsion? Nuclear thermal rockets, which heat propellant using a nuclear reactor, can achieve exhaust velocities about twice as high as chemical rockets. That helps, but not enough. You're still looking at tens of thousands of years to reach the nearest star. Nuclear pulse propulsion, the idea of detonating nuclear bombs behind a spacecraft to push it forward, was studied in Project Orion in the 1950s and 60s. Theoretically, it could achieve velocities of 3 to 5% of light speed. At 5% of light speed, the journey to Proxima Centauri would take about 85 years. Getting closer to a human lifespan, but still requiring an astronaut to spend their entire adult life in transit. But there's a catch. Project Orion would require thousands of nuclear bombs. It would create massive radioactive contamination during launch. It's banned by the Partial Nuclear Test Ban Treaty of 1963. And we've never actually built or tested a nuclear pulse spacecraft. It's not a technology we have, it's a technology we might theoretically develop, if we were willing to accept catastrophic environmental consequences. What about antimatter? Antimatter is the ultimate fuel. When matter and antimatter collide, they annihilate completely, converting 100% of their mass into energy, according to E equals mc squared. This is millions of times more efficient than nuclear reactions, which convert only about 0.7% of mass into energy. With antimatter propulsion, we could theoretically achieve velocities of 50% of light speed or more. The journey to Proxima Centauri would take less than 10 years. But here's the problem. We can't make antimatter. I mean, we can. We make tiny amounts in particle accelerators, but the total amount of antimatter ever produced by humanity is measured in nanograms. Not kilograms, not grams, nanograms, billionths of a gram. To propel an interstellar spacecraft, you'd need tons of antimatter. And producing a single gram of antimatter with current technology would require more energy than the entire world consumes in a year. The cost has been estimated at $62.5 trillion per gram. A spacecraft requiring 10 tons of antimatter would cost more than the entire GDP of human civilization for the next several centuries. Antimatter isn't a solution, it's a fantasy. What about solar sails? Solar sails use the pressure of sunlight to accelerate. No fuel required, the light itself provides the push. The Planetary Society has demonstrated that solar sails work with their light sail missions. But solar sails have a fundamental problem. The intensity of sunlight decreases with the square of the distance from the Sun. By the time you're at Jupiter's orbit, sunlight is only 4% as intense as at Earth. By Pluto's orbit, it's 0.1%. For interstellar travel, solar sails would need to be accelerated very close to the Sun, then coast for the rest of the journey. The Breakthrough Starshot project proposes using powerful ground-based lasers to accelerate tiny probes to 20% of light speed. But tiny is the key word. These probes would weigh about 1 gram each. They could carry a camera and a transmitter, but nothing else. No humans, no life support. Just a camera chip the size of a postage stamp. And even then, the laser array required would be kilometers across and require gigawatts of power. It would cost billions of dollars, and it would only work for gram-scale probes. For anything human-sized, anything that could carry people, supplies, life support systems, solar sails and laser propulsion simply don't scale up. So we're stuck. Chemical rockets can't do it. Nuclear thermal can't do it. Nuclear pulse might theoretically work, but would be environmentally catastrophic. Antimatter is impossibly expensive. Solar sails only work for tiny probes. Every propulsion technology we have, or can reasonably imagine, fails to solve the interstellar travel problem for human beings. But propulsion isn't even the biggest problem. Let's talk about what space actually does to the human body. The longest any human has spent in space continuously is 437 days. Cosmonaut Valery Polyakov aboard the Mir space station in 1994 to 1995. Even shorter missions of 6 to 12 months cause significant health problems. Bone loss. In microgravity, astronauts lose about 1 to 2% of their bone density per month. Over a multi-year mission, this could leave astronauts with bones so fragile they'd shatter upon return to any gravitational environment. Muscle atrophy. Without gravity to work against, muscles waste away. Astronauts exercise for 2+ hours every day on the International Space Station and still return to Earth significantly weaker. Vision problems. About 60% of astronauts on long-duration missions experience vision changes, sometimes permanent. The leading theory is that fluid shifts in microgravity increase pressure on the optic nerve. Radiation exposure. Earth's magnetic field protects us from most cosmic radiation. Outside that shield, astronauts are exposed to high-energy particles that increase cancer risk and may cause cognitive decline. Psychological effects. Isolation, confinement, and separation from Earth take a toll. The psychological challenges of a multi-decade journey with no possibility of return are essentially unknown. Immune system changes. The immune system behaves differently in space, becoming simultaneously overactive, causing allergies and inflammation, and less effective at fighting infections. These aren't minor inconveniences. These are serious, potentially fatal problems that we don't know how to solve. A 42-year journey to Proxima Centauri at 10% of light speed, the fastest realistic option we've discussed, would expose astronauts to 42 years of cosmic radiation. The cancer risk alone would be enormous. Cognitive decline from radiation damage to the brain could render the crew incapable of operating the spacecraft. 42 years of bone and muscle loss. Even with artificial gravity, which we haven't built, the long-term effects are unknown. 42 years of isolation. No real-time communication with Earth. At 4.24 light years, each message would take 4.24 years to arrive. The crew would be truly alone. 42 years of mechanical systems that cannot fail. A spacecraft that must operate without major repairs for nearly half a century, using only the tools and materials on board. This isn't speculation. This is what we know from studying astronauts who've spent mere months in space. The problems multiply with time. And we haven't even talked about the destination. Let's say, hypothetically, that we somehow solve all of these problems. We invent a new propulsion system. We figure out how to protect astronauts from radiation. We develop artificial gravity. We solve the psychological challenges. And after 42 years, we arrive at Proxima Centauri b, the closest known exoplanet in the habitable zone of another star. What do we find? Proxima Centauri b orbits a red dwarf star. Red dwarfs are very different from our Sun. They're smaller, cooler, and much more active. Proxima Centauri regularly produces powerful stellar flares that would bathe any close-orbiting planet in deadly radiation. Let me explain just how hostile the Proxima Centauri system really is. Proxima Centauri is an M-type red dwarf star with about 12% of the Sun's mass and 0.15% of its luminosity. To receive Earth-like amounts of energy, a planet must orbit very close to such a dim star, much closer than Mercury orbits our Sun. Proxima Centauri b orbits at just 0.05 astronomical units from its star, with an orbital period of only 11.2 days. At this distance, it's well within the habitable zone, the region where liquid water could theoretically exist on the planet's surface. But proximity to a red dwarf comes with serious problems. First, tidal locking. At such close distances, gravitational forces cause the planet to rotate synchronously with its orbit. One side always faces the star, eternal day, while the other side always faces away, eternal night. The day side could be scorching hot, with temperatures high enough to boil away any surface water. The night side could be freezing cold, with temperatures low enough to freeze any atmosphere. The only habitable region might be a narrow terminator zone between day and night, a thin ring around the planet where temperatures are moderate. Even this is optimistic. Without proper atmospheric circulation, the temperature differences could be extreme enough to make the entire planet uninhabitable. Second, stellar flares. Red dwarfs are notoriously active stars. Proxima Centauri produces frequent flares that can briefly increase its brightness by a factor of 10 or more. In 2019, astronomers detected a superflare from Proxima Centauri, one of the most powerful stellar flares ever observed from any star. This single event was about 100 times more powerful than any flare ever recorded from our Sun. Such flares blast the planet with intense X-rays and ultraviolet radiation. They also produce coronal mass ejections, clouds of charged particles that can strip away a planet's atmosphere over time. The planet is tidally locked, meaning one side always faces the star, while the other side always faces away. One hemisphere is in permanent daylight, the other is in permanent darkness. The habitable zone, if it exists at all, would be a narrow strip along the terminator line between day and night. The planet has no confirmed atmosphere. Recent observations suggest it may have been stripped away by the star's intense flares. There's no evidence of water, no evidence of life, no evidence that the planet could support human colonization. Third, the lack of an atmosphere. Observations with the James Webb Space Telescope and other instruments have failed to detect any significant atmosphere around Proxima Centauri b. This could mean the atmosphere was stripped away by stellar activity. The planet never had a substantial atmosphere. Our observations aren't sensitive enough yet to detect a thin atmosphere. Without an atmosphere, the surface would be exposed directly to stellar radiation and cosmic rays. There would be no greenhouse effect to moderate temperatures. The planet would be more like the Moon than like Earth. Fourth, the lack of a magnetic field. We don't know if Proxima Centauri b has a global magnetic field like Earth's. If it doesn't, there would be no protection against charged particles from the star or from cosmic sources. Earth's magnetic field deflects most of the solar wind and cosmic rays, allowing life to exist on the surface. Without such protection, the surface of Proxima Centauri b would be sterilized by radiation. So what would colonists find if they arrived at Proxima Centauri b? Probably a dead world. A planet with no air, no water, no life. A frozen night side and a baked day side. A surface bombarded by radiation from an unstable star. Not exactly the paradise that science fiction promised us. After 42 years of travel, after investing trillions of dollars, after sending humans on a journey from which they could never return, we might arrive at a dead, irradiated rock. And Proxima Centauri b is the closest potentially habitable exoplanet. Everything else is further away, much further. The next nearest candidate is Ross 128b, about 11 light years away. At 10% of light speed, that's 110 years of travel. TRAPPIST-1, with its system of 7 Earth-sized planets, is 39 light years away. That's 390 years of travel. Kepler 442b, one of the most Earth-like exoplanets known, is 112 light-years away. Over 1,000 years of travel. We're not talking about exploration. We're talking about exodus. One-way journeys spanning centuries, with no guarantee of finding anything habitable at the end. This is why the Voyager missions are so important and so depressing. Voyager 1 and Voyager 2 have been traveling for nearly 50 years. They've covered about 24 billion kilometers. They've passed the heliopause and entered interstellar space. And they've traveled less than 0.06% of the distance to the nearest star in 48 years. At the fastest speeds humanity has ever achieved, less than 0.1% of the way. The Voyagers will continue traveling for millions of years, long after their nuclear power sources die and their transmitters fall silent. They'll drift through the galaxy as dead, frozen relics. Voyager 1 will pass within 1.6 light-years of the star Gliese 445 in about 40,000 years. It won't stop there. It will just pass by, a tiny speck of metal moving through the vastness. In about 296,000 years, Voyager 2 will pass within 4.3 light-years of Sirius, the brightest star in our night sky. These aren't destinations. These are coincidences of trajectory. The Voyagers aren't going anywhere. They're just going away. And they're the best we've ever done. Now let me address the obvious objections. But technology always improves. 100 years ago we couldn't fly. Now we can travel to the moon. In another 100 years, we'll solve interstellar travel. This argument sounds reasonable, but it misunderstands the nature of the problem. The progression from horse-drawn carriages to automobiles to aeroplanes to rockets wasn't a progression of overcoming impossible physics. It was a progression of engineering improvements within the boundaries of physics. Interstellar travel isn't an engineering problem, it's a physics problem. The speed of light is a hard limit. It's not a barrier we can break with better technology. It's a fundamental property of space-time. Nothing with mass can ever reach or exceed it. And even if we could travel at the speed of light, which we can't because we have mass, the journey to Proxima Centauri would still take 4.24 years. This is different from past technological barriers. When people said humans will never fly, they were wrong because flight didn't violate physics. When people said we'll never reach the moon, they were wrong because rockets were physically possible. When I say humans will probably never travel to other stars, I'm not making a pessimistic prediction. I'm describing physical constraints that no amount of technology can overcome. But what about warp drives? What about wormholes? The Alcubierre warp drive is a theoretical solution to Einstein's field equations that would allow faster-than-light travel by contracting space in front of a spacecraft and expanding it behind. It requires negative energy density, a quantity that may not exist in nature. If it does exist, we don't know how to create or harness it. The original calculations suggested that operating a warp drive would require more energy than exists in the observable universe. More recent papers have reduced the energy requirements, but they're still astronomical. And the fundamental problem of negative energy remains unsolved. Wormholes, shortcuts through space-time, are another theoretical possibility. But creating a wormhole would require exotic matter with negative mass, which has never been observed and may not exist. Even if we could create a wormhole, we don't know how to stabilize it or make it large enough for a spacecraft to pass through. These aren't technologies, they're mathematical curiosities. They might as well be magic for all the practical use they offer. Relying on warp drives and wormholes to save interstellar travel is like relying on time travel to fix your mistakes. It's not a plan, it's a hope. What about generation ships? Humans travel for centuries, reproducing along the way until their descendants arrive at the destination. This is actually the most plausible scenario for interstellar colonization. Not fast travel, but slow travel over many generations. But let's think about what this actually requires. A generation ship would need to be entirely self-sufficient for centuries, not years, centuries. It would need to produce its own food, recycle its own water and air, maintain its own machinery, and sustain a viable human population, all without any resupply from Earth. The minimum viable population for genetic diversity is estimated at around 10,000 people. Some studies suggest it could be as low as 500 with careful genetic management, but the risks of inbreeding, genetic drift, and founder effects are significant. So we're talking about a spacecraft that can support hundreds or thousands of people for hundreds of years. The International Space Station, which supports 6 to 7 people and requires constant resupply from Earth, cost over $150 billion to build and operate, and it's not remotely self-sufficient. Scaling up to a self-sufficient habitat for thousands of people over centuries would require, what? Trillions of dollars? Tens of trillions? More than human civilization has ever produced. And that's before propulsion, before radiation shielding, before solving all the other problems we've discussed. Generation ships aren't impossible in the way that faster-than-light travel is impossible, but they're so far beyond their current capabilities that they might as well be. We couldn't build one today. We probably couldn't build one in 100 years. Maybe, with revolutionary advances in technology and unprecedented global cooperation, we could build one in 500 years. But here's the dark irony. If we could build a generation ship, why would we want to? The journey to even the nearest star would take centuries. During those centuries, technology on Earth would continue to advance. A faster ship launched 200 years later might arrive before the generation ship does. This is the wait calculation, the argument that it's always better to wait for faster technology rather than launching now with slow technology. The logical conclusion is to wait forever. And even if we launched a generation ship, what would the passengers experience? They would be born, live, and die inside a metal can hurtling through empty space. They would never see Earth. They would never see their destination during their lifetimes. Their only experience of the universe would be the interior of a spacecraft and the stars visible through portholes. Their children would experience the same, and their children's children. Generation after generation, living and dying in transit, for a destination that only their distant descendants would ever reach. Is that ethical? Bringing children into existence specifically to live and die on a spacecraft, without their consent, for a goal they'll never see achieved? Let me explore this ethical dimension more deeply, because I think it's crucial and often overlooked. A generation ship would create a population of people who never chose to be there. The original crew might volunteer, accepting the mission knowing they'll never see the destination. But their children, their grandchildren, their great-great-great-grandchildren? These people would be born into a metal cylinder hurtling through the void. They would have no choice in the matter. Their entire lives would be predetermined by a decision made centuries before their birth. They would never feel wind on their faces, never swim in an ocean, never walk through a forest, never see a sunset except through old recordings and simulations. Their universe would be the interior of a spacecraft, perhaps a few kilometers across at most. Compared to Earth, with its vast oceans and continents, its mountains and valleys, its billions of unique ecosystems, a generation ship would be a prison. Would the inhabitants accept their fate, or would they rebel? Would they resent the ancestors who condemned them to this existence? Would they try to turn the ship around, assuming that was even possible? There's a science fiction trope where generation ship crews forget their mission entirely. Over centuries, the original purpose is lost. The inhabitants come to believe the ship is their universe, that there is nothing outside. They develop religions and social structures suited to their confined environment. When they finally arrive at their destination, they don't understand what it means. This might seem far-fetched, but consider, how much do you really know about your ancestors from 10 generations ago? How much of their worldview have you inherited? How much have you forgotten? A 400-year journey would span roughly 15 to 20 generations. The people who arrive would be as distant from the original crew as we are from people living in the 1600s. They would speak a different language, hold different values, have different priorities. Would they even want to colonize the destination world? Or would they prefer to stay on the ship, which has been their home for their entire cultural memory? Generation ships might solve the physics problem of interstellar travel, but they create a whole new category of human problems that we have no idea how to address. These are questions we've never had to ask before, and we have no good answers. What about sending our minds instead of our bodies? Digital consciousness uploaded to computers? This is perhaps the most viable path to interstellar travel, if you're willing to accept that the thing that arrives isn't really you. A spacecraft carrying digital minds could be much smaller and lighter than one carrying biological humans. It wouldn't need life support, food, water, or air. It could be accelerated to higher velocities with the same amount of energy. And digital minds could, in theory, be shut down for the journey and restarted upon arrival, experiencing no subjective time during transit. But mind uploading requires technology we don't have, and might never have. We don't understand consciousness. We don't know how to read the complete state of a human brain. We don't know if a digital copy would actually be conscious or just a very sophisticated imitation. And even if we could upload minds, there's a philosophical question. Is the upload you? If you upload your mind to a computer and then die, did you survive? Or did you create a copy that thinks it's you, while the real you ceased to exist? These aren't trivial questions. They go to the heart of what we mean by identity and continuity of self. Relying on mind uploading to solve interstellar travel requires us to solve the hard problem of consciousness, something neuroscientists and philosophers have been working on for decades without clear progress. It's not a near-term solution. It might not be a solution at all. Let me take a step back and address what I think is the real issue here. Why do we want to travel to other stars? The usual answers are exploration, survival, and expansion. Let's examine each. Exploration. We want to see what's out there. We're curious. It's human nature. This is valid. But we can explore without sending humans. Robotic probes, like the Voyagers themselves, can visit other star systems, take pictures, collect data, and transmit it back to Earth. The Breakthrough Starshot project proposes exactly this. Tiny probes accelerated to 20% of light speed that could reach Proxima Centauri in about 20 years and transmit images back. Sending robots is vastly easier than sending humans. If exploration is the goal, robots are the answer. Survival. We want to ensure humanity's long-term survival by spreading to other worlds. If Earth is destroyed, we need a backup. This is the strongest argument for interstellar colonization. But is it realistic? The threats to humanity on Earth, asteroid impacts, supervolcanic eruptions, climate change, nuclear war, pandemics, are all more easily addressed by protecting Earth than by escaping to the stars. It would be far cheaper and easier to build asteroid deflection systems, develop pandemic response capabilities, and transition to sustainable energy than to build interstellar colonies. And even if we did establish colonies on other worlds, they would be so far away that they couldn't help Earth in a crisis. A colony at Proxima Centauri couldn't send aid. It would take years just for a message to arrive. For survival purposes, colonies in our own solar system, on Mars, on the moons of Jupiter and Saturn, in orbital habitats, would be far more practical. They're much closer, allowing for mutual support. And they're within reach of our current technology. Interstellar colonies are not survival insurance. They're expansion for its own sake. Expansion. We want to spread throughout the galaxy. It's our destiny. We're a species that explores and colonizes. This is essentially an ideological argument, not a practical one. We want to colonize the stars because colonizing is what humans do. But should we? The history of human colonization on Earth is not exactly glorious. It involved the displacement and destruction of indigenous peoples, the exploitation of resources, and the imposition of one culture over another. Interstellar space is, as far as we know, empty of intelligent life. So we wouldn't be displacing anyone, but we'd be spreading human problems, our conflicts, our environmental destruction, our inequalities to new worlds. Is expansion inherently good, or is it just something we're biologically driven to do, regardless of whether it's wise? I don't have answers to these questions, but I think they're worth asking before we commit trillions of dollars and centuries of effort to interstellar colonization. Here's my honest assessment of humanity's future in space. In the near term, the next 100 years, we will probably establish permanent bases on the Moon and Mars. These will be research outposts at first, similar to Antarctic stations. Eventually, they may grow into small colonies. In the medium term, the next 500 years, we may expand throughout the solar system. Mining operations in the asteroid belt, colonies on the moons of Jupiter and Saturn, orbital habitats in various locations, thousands or millions of people living off Earth, but all within the solar system. In the long term, thousands of years from now, we might, possibly, send robotic probes to other star systems. Small, fast probes carrying cameras and instruments. These would take decades to arrive and decades more to send back their findings. But human interstellar travel? Humans physically traveling to other star systems? I don't think it will happen. Not because I'm pessimistic, but because I've looked at the physics, the engineering, the biology, and the economics. The universe is simply too big. The distances are too vast. The energy requirements are too extreme. The timescales are too long. We are not destined to colonize the galaxy. We are destined to live and die in this solar system, on this tiny rock orbiting this ordinary star. And you know what? That's okay. The solar system is enormous. There are entire worlds to explore. Mercury, Venus, Mars, the moons of Jupiter and Saturn, the asteroids, the Kuiper Belt. There's enough space for trillions of humans to live comfortably for billions of years. We don't need other star systems. We have a perfectly good one right here. And from here, we can still study the universe. We can build giant telescopes that image exoplanets directly. We can send robotic probes to explore nearby stars. We can search for signals from other intelligences. We can know the universe without physically visiting every part of it. That's not a failure. That's an acknowledgement of reality. The Voyager spacecraft carry golden records with greetings from Earth. The assumption was that someday, somewhere, someone might find them. But here's the truth. No one will find them. The Voyagers will drift through interstellar space for millions of years. They will pass countless stars at enormous distances. They will never enter another solar system. They will never be intercepted by another civilization. Space is too big. The Voyagers are too small. The odds of a random object being found in the vastness of space are effectively zero. The golden records were never really for aliens. They were for us. They were a symbol of our hopes, our dreams, our desire to reach beyond ourselves. And in that sense, they succeeded. They inspired generations of scientists and dreamers. They gave us a vision of humanity as a spacefaring species. But symbols are not reality. And the reality is that the Voyagers have proven, more clearly than anything else, that interstellar travel is beyond our reach. In 48 years, moving faster than any human has ever travelled, they've covered less than 0.06% of the distance to the nearest star. That's not progress. That's a demonstration of impossibility. I want to be clear about what I'm not saying. I'm not saying we should give up on space exploration. We shouldn't. The solar system is vast and largely unexplored. There's plenty of work to do right here. I'm not saying we should stop dreaming about the stars. Dreams inspire us, motivate us, push us to achieve things we never thought possible. I'm not saying that some future breakthrough might not change everything. Physics has surprised us before. It might surprise us again. But I am saying that based on everything we currently know about physics, about engineering, about biology, about economics, interstellar travel for human beings is not something we should expect or plan for. It's not coming in our lifetimes. It's probably not coming in our civilization's lifetime. It might not come at all. And that's a truth we need to make peace with. We are a species that evolved on a single planet. Our bodies are adapted to Earth's gravity, Earth's atmosphere, Earth's magnetic field. We are creatures of this world in ways we barely understand. The universe did not design us to live among the stars. It designed us to live here, on this beautiful, fragile, irreplaceable world. Maybe that's enough. Maybe it has to be. Let me tell you about a concept called the Great Filter. The Great Filter is a proposed explanation for the Fermi paradox, the question of why we haven't detected any signs of extraterrestrial intelligence, despite the vast size and age of the universe. The idea is that somewhere in the development of life and civilization, there's a barrier that almost all species fail to pass, a filter that prevents them from becoming visible to other civilizations. The filter could be behind us. Maybe life itself is extremely rare. Maybe intelligent life is extremely rare. Maybe we're one of the first civilizations in the galaxy, and that's why we don't see others. Or the filter could be ahead of us. Maybe civilizations inevitably destroy themselves through war, environmental collapse, or some other catastrophe before they can spread to the stars. But here's another possibility that rarely gets discussed. Maybe the Great Filter is interstellar travel itself. Maybe every civilization that evolves reaches a point where they realize that the stars are out of reach. The distances are too great. The physics is insurmountable. They're trapped in their home solar system, no matter how advanced their technology becomes. And maybe that realization changes something. Maybe it changes how a civilization views itself, its future, its priorities. We've always assumed that advanced civilizations spread throughout the galaxy. But what if they don't? What if they can't? What if we're not alone in the universe, but every civilization is alone in its own solar system, separated by unbridgeable gulfs of space? This would explain the Fermi paradox without requiring extinction. Civilizations exist, they just can't reach each other. They're all sitting at home, looking up at the stars, wondering if anyone else is out there. If this is true, it changes everything about how we think about our place in the universe. We're not a young species waiting to grow up and join a galactic community. We're not pioneers about to embark on a grand expansion. We're not destiny's children, fated to colonize the cosmos. We're just here, on this planet, in this solar system, for as long as we last. And maybe, somewhere out there, other civilizations are sitting on their own planets, in their own solar systems, thinking the same thoughts. Let me explore this idea further, because I find it strangely comforting. If interstellar travel is impossible, not just for us, but for any biological species, then the galaxy isn't empty because civilizations destroy themselves. It's empty because civilizations can't spread. This has profound implications. First, it means that any intelligent life we might someday detect is not a threat. They can't come here. They can't invade. They can't colonize. The vast distances that trap us also protect us. Second, it means that we have plenty of time. There's no galactic race to claim territory. There's no competition for resources beyond our own solar system. We can develop at our own pace without fear of being overtaken by more advanced species. Third, it means that communication becomes more valuable than travel. If we can't visit other civilizations, we can still talk to them. Radio waves travel at the speed of light. A message to Proxima Centauri would take 4.24 years. A message to a civilization 100 light-years away would take 100 years. That's slow by human standards, but it's infinitely faster than sending physical spacecraft. Imagine a galaxy filled with civilizations that can communicate but not visit. A cosmic community of minds, separated by unbridgeable distances, exchanging knowledge and culture across the light years. Each civilization would be isolated physically, but connected intellectually. They would share discoveries, art, philosophy, not people or goods, but ideas. It's not the Star Trek future we dreamed of, but it's not dystopian either. It's just different. A universe of pen pals rather than neighbors, of long-distance relationships that span centuries, of knowledge shared across voids that bodies can never cross. Maybe that's our future. Not starships and colonies, but radio telescopes and patience. Not reaching the stars, but hearing them. That's a lonelier vision than Star Trek or Star Wars promised us, but it might be closer to the truth. So where does this leave us? Voyager 1 and Voyager 2 are still out there, still traveling, still sending back data, for now. Their nuclear power sources are slowly dying. By 2025 or so, they won't have enough power to run any scientific instruments. By 2036, they probably won't be able to communicate with Earth at all. After that, they'll go silent. They'll drift through interstellar space as dead relics, carrying their golden records with them, messages that will never be received. Greetings that will never be heard. In about 40,000 years, Voyager 1 will pass within 1.6 light-years of the star Gliese 445. It won't stop. It won't even slow down. It will just sail past, a tiny piece of metal in an ocean of emptiness. And here on Earth, we'll continue living our lives, building our cities, having our wars, making our art, falling in love, growing old, dying, being replaced by new generations who will do the same. The stars will continue shining, other worlds will continue orbiting other suns, and we'll continue watching them from here, dreaming of what might be, knowing that we'll never make the journey. Is that sad? Maybe. But there's also something beautiful about it. We are, as far as we know, the only place in the universe where matter has organized itself to contemplate its own existence. The only place where atoms have arranged themselves into patterns complex enough to ask questions about the nature of reality. We're rare. We're precious. We're here. And this planet, this tiny blue dot orbiting an ordinary star in an ordinary galaxy, is our home. Our only home. The only home we're ever likely to have. Maybe, instead of dreaming about escaping to the stars, we should focus on taking care of what we have. Not because the stars are unimportant, but because Earth is more important. We're not going anywhere. The Voyagers proved that. The physics proves that. The mathematics proves that. We're here. We're home. This is it. And maybe, just maybe, that's not a tragedy. Maybe it's just the truth. The universe is vast and beautiful and full of wonders. And we get to experience it from this one particular vantage point, on this one particular world, during this one particular moment in cosmic history. That's not nothing. That's everything. The Voyagers are still out there, carrying pieces of us into the void. They'll travel for millions of years, long after humanity is gone. They're our message in a bottle, thrown into an infinite ocean. No one will find them. No one will read our greetings. No one will listen to our music. But we sent them anyway, because that's who we are. We reach for the stars even when we know we can't touch them. And there's something magnificent about that. Something hopeful and tragic and deeply, profoundly human. We are dreamers, stuck on a rock, imagining ourselves among the stars. And maybe that's the most human thing of all. Not the journey, not the arrival, not the colonization, just the dream. The dream that there might be more. The dream that we might, somehow, transcend our limitations. The dream that the universe might, against all odds, have a place for us beyond this small, fragile world. The Voyagers carry that dream. They'll carry it forever, sailing through the darkness, going nowhere and everywhere at once. And back here on Earth, we'll keep looking up, keep wondering, keep hoping, because that's what humans do. Even when we know the truth, even when the numbers don't add up, even when the distances are impossible, we dream anyway. And maybe that's enough. Maybe that's all there ever was. The dream of the stars, the reality of Earth, and the vast, silent gulf between. Now let me add some important context that often gets overlooked in these discussions. The Voyager spacecraft weren't designed for interstellar travel. They were designed to explore the outer planets, Jupiter, Saturn, Uranus, and Neptune. The fact that they're now in interstellar space is a bonus, not the mission objective. So it might seem unfair to use them as proof that interstellar travel is impossible. After all, they're using 1970s technology. They weren't optimized for interstellar velocities. But here's the thing. Even with modern technology, we can't do much better. The Parker Solar Probe, launched in 2018, is the fastest spacecraft ever built. At its closest approach to the Sun, it reaches speeds of about 700,000 kilometers per hour. That's impressive. It's about 11 times faster than Voyager. But at that speed, the journey to Proxima Centauri would still take about 6,500 years. And the Parker Solar Probe achieves its speed by falling toward the Sun, using the Sun's gravity to accelerate. This technique doesn't work for interstellar travel, where you're moving away from the Sun. For a spacecraft leaving the solar system, the theoretical maximum velocity using chemical rockets is about 20 kilometers per second. That's actually slower than Voyager, which got gravitational assists from Jupiter and Saturn. So modern technology doesn't help. We've had 48 years of technological progress since the Voyager's launched, and our best spacecraft is still too slow by a factor of thousands. Let's talk about what would actually be needed for interstellar travel. The energy requirements are staggering. The kinetic energy of a moving object is given by E equals 1/2 mv squared. If you want to accelerate a 1,000 kilogram spacecraft, about the mass of a small car, to 10% of the speed of light, you need E equals 1/2 times 1,000 kilograms times 30 million meters per second squared. E equals 4.5 times 10 to the 17th power joules. That's 450 petajoules. For comparison, the total energy consumption of the United States in 2022 was about 100 exajoules, roughly 220 times this amount. So accelerating a small car to 10% of light speed requires about 0.5% of the entire annual energy consumption of the United States. But a spacecraft carrying humans would weigh far more than 1,000 kilograms. A minimal crewed spacecraft might weigh 10,000 to 100,000 kilograms. A generation ship for thousands of people might weigh millions of kilograms. And you need energy not just to accelerate, but also to decelerate at the destination, unless you're willing to fly past at 10% of light speed without stopping. For a crewed spacecraft that accelerates to 10% of light speed and then decelerates upon arrival, you're looking at energy requirements comparable to the entire annual energy output of human civilization. Where does that energy come from? Not from chemical rockets. The energy density of chemical fuels is far too low. Not from nuclear fission. Even with perfect conversion of uranium to energy, you'd need to carry thousands of tons of fuel. Nuclear fusion is better. The fusion of hydrogen to helium releases about 0.7% of the mass as energy. A fusion-powered spacecraft could theoretically achieve the required velocities. But we don't have fusion rockets. We barely have fusion power plants, none that produce net energy. The technology is decades away at minimum. Antimatter, as I mentioned earlier, would be ideal, but we can't produce it in anywhere near the quantities needed. So the energy problem alone is essentially unsolved. We don't have any practical way to generate the energy required for interstellar travel. Let me talk about communication. Even if we could send a spacecraft to another star, we'd want to communicate with it. That presents its own challenges. Radio signals travel at the speed of light. At the distance of Proxima Centauri, a radio signal would take 4.24 years to arrive. So if you sent a spacecraft to Proxima Centauri and it arrived after a 42-year journey, any message it sent back would take another 4.24 years to reach Earth. That's not insurmountable, but consider this. The Voyager spacecraft, at their current distance of about 24 billion kilometers, transmit at about 160 bits per second. That's slower than a dial-up modem from the 1990s. The signal strength of a radio transmission decreases with the square of the distance. Proxima Centauri is about 1,700 times farther away than Voyager. That means a signal from Proxima Centauri would be about 2.9 million times weaker. To receive such a signal, you'd need either a much more powerful transmitter on the spacecraft, a much larger receiving antenna on Earth, or both. The Deep Space Network, which communicates with our current spacecraft, uses antennas up to 70 meters in diameter. To receive signals from Proxima Centauri at the same data rate as Voyager, you'd need an antenna about 120 kilometers in diameter. That's not a typo. 120 kilometers. We could use laser communication instead of radio, which allows for more focused beams. But even with lasers, the distances involved are enormous, and maintaining communication with an interstellar spacecraft would require a massive infrastructure investment. Now let's talk about navigation. Navigating to another star system is not like navigating on Earth, or even in the solar system. Stars move. The Alpha Centauri system is currently 4.24 light-years away, but it's moving relative to the Sun at about 25 kilometers per second. Over the course of a 42-year journey at 10% of light speed, the target would move by about 33 billion kilometers, roughly the distance from the Sun to Neptune. A spacecraft would need to continuously adjust its trajectory to account for this motion. And since communication with Earth would be time-delayed by years, the spacecraft would need to make these calculations autonomously. Furthermore, interstellar space is not completely empty. There are gas particles, dust grains, and larger objects. At 10% of light speed, even a tiny dust grain would impact with enormous energy. A grain of sand would hit like a bomb. The spacecraft would need shielding against these impacts. But shielding adds mass, which increases the energy needed for acceleration. The Breakthrough Starshot project, which proposes sending tiny probes to Proxima Centauri at 20% of light speed, acknowledges that some probes will be destroyed by dust impacts. They plan to send thousands of probes, hoping that at least some survive. For a crewed spacecraft, that approach obviously won't work. You need certainty, not statistics. Let me talk about one more factor that rarely gets discussed: politics and economics. An interstellar mission would be the most expensive project in human history, by a lot. The Apollo program, which landed humans on the Moon, cost about $280 billion in 2023 dollars. The International Space Station has cost about $150 billion over its lifetime. An interstellar mission would cost trillions of dollars, possibly tens of trillions, spread over decades or centuries. Who pays for this? No single nation could afford it. It would require unprecedented international cooperation, the kind we've never achieved for any project, ever. And for what return? The moon landings produce scientific knowledge, national prestige, and technological spin-offs. The ISS has advanced our understanding of human spaceflight and conducted valuable research. But an interstellar mission would produce a spacecraft that arrives somewhere 50 or 100 years after launch, by which point the people who funded it would be dead. The society that built it would be completely different. The original motivations might be forgotten. It's hard to imagine any political system maintaining commitment to a project over such timescales. Governments change, priorities shift, economic conditions fluctuate. The pyramids of Egypt took about 20 years to build, and that required an entire kingdom's resources focused on a single project under autocratic rule. An interstellar mission would require similar focus maintained for centuries. Under what political system? With what economic model? These aren't engineering problems, they're social problems, and we don't know how to solve them. So when I say that interstellar travel is probably impossible, I'm not just talking about physics and engineering. I'm talking about the full scope of what would be required. The energy is beyond our current capabilities. The propulsion technology doesn't exist. The life support for long-duration missions is unsolved. The radiation protection is inadequate. The communication is challenging. The navigation is difficult. The economics are prohibitive. The politics are impractical. Any one of these problems would be daunting. Together, they're overwhelming. Could we solve all of them eventually? Maybe. In thousands of years, with technologies we can't currently imagine, perhaps interstellar travel becomes feasible. But that's speculation, not planning. That's hoping for miracles, not engineering solutions. For the foreseeable future, the next few centuries at least, we're stuck in this solar system. And the Voyagers prove it. After 48 years of travel at record-breaking speeds, they're barely out the door. Let me offer a different perspective on all of this. Maybe being confined to the solar system isn't a tragedy. Maybe it's an opportunity. The solar system is vast. There are 8 planets, dozens of moons, millions of asteroids, billions of comets. There's enough real estate for trillions of human beings. Mars has a surface area equal to all the land on Earth. The asteroid belt contains enough material to build thousands of space habitats. The outer solar system has water ice in quantities that dwarf Earth's oceans. If we focused our efforts on developing the solar system rather than dreaming about the stars, we could establish permanent human settlements on the Moon and Mars within the next century, build mining operations in the asteroid belt, providing resources for further expansion, construct orbital habitats that could house billions of people in comfortable conditions, develop the moons of Jupiter and Saturn, accessing vast reserves of water and organic compounds, create a civilization that spans the solar system, connected by trade and communication, diverse in culture and outlook. This isn't science fiction. This is achievable with extensions of current technology. We know how to build rockets. We know how to keep people alive in space. We know how to construct large structures in orbit. The solar system is ours for the taking, if we choose to take it. And from the solar system, we can still reach out to the stars, just not physically. We can build giant telescopes that directly image planets around other stars. We can analyze their atmospheres for signs of life. We can send robotic probes to nearby systems. We can search for signals from other civilizations. We can broadcast our own signals into the cosmos. We can know the universe without physically colonizing it. That's not a consolation prize. That's an incredible opportunity. We're the first generation that has the technology to seriously explore our own solar system. We're the first generation that can see planets around other stars. We're the first generation that can search the skies for evidence of other minds. This is an extraordinary moment in human history. We should appreciate it rather than lamenting the journeys we can't make. The Voyagers are often described as ambassadors to the stars. They carry greetings from Earth, images of our world, sounds of our civilization. But they're not really ambassadors. Ambassadors go somewhere and meet someone. The Voyagers are going nowhere and will meet no one. They're time capsules, artifacts, monuments. They're proof that we existed, proof that a species called humanity once lived on a planet called Earth, looked up at the stars and wondered. In billions of years, the sun will expand into a red giant and vaporize the Earth. Every trace of human civilization on our planet will be destroyed. But the Voyagers will still be out there, drifting through interstellar space. They'll outlast us. They'll outlast Earth. They'll outlast the sun. They're our most permanent creation, our longest-lasting legacy, and they carry with them a message. We were here. We dreamed. We reached. Maybe that's enough. Maybe that's all any species gets. Not the stars themselves, but the dream of the stars. Not the journey, but the desire to journey. Not arrival, but aspiration. The universe is vast and mostly empty. Most places are uninhabitable. Most distances are uncrossable. Most stars will never be visited by anyone. But consciousness exists, here, now, on this tiny world orbiting this ordinary star. And consciousness can imagine, it can dream, it can create. The Voyagers are products of that imagination, their dreams made metal. And somewhere out there, sailing through the darkness, they carry those dreams forward, forever. That's not failure, that's transcendence, not of space, but of time, not of distance, but of mortality. We sent a part of ourselves into eternity. That's not nothing, that's everything. So here's what I want you to take away from this. Space is hard. Interstellar travel is almost certainly impossible for biological humans. We will probably never leave this solar system, but that's okay. We have a solar system full of wonders to explore. We have telescopes that can see to the edge of the observable universe. We have minds that can understand physics, chemistry, biology, mathematics. We can know the cosmos, even if we can't physically traverse it. And we can send our dreams into the void, even if we can't follow them ourselves. The Voyagers are out there, right now, 24 billion kilometers from home, and counting. They'll never reach another star. They'll never be found by another civilization. They'll drift in silence for billions of years. But they carry with them the essence of what we are: curious, ambitious, hopeful. They carry our best selves into infinity. And that's worth celebrating. Not mourning, celebrating. Because the dream matters, even if it never comes true. The reach matters, even if we never grasp. The attempt matters, even if we never succeed. Let me tell you about the last signals we'll receive from Voyager. Right now, both Voyagers are powered by radioisotope thermoelectric generators, RTGs, devices that convert heat from decaying plutonium-238 into electricity. These generators produce less power every year as the plutonium decays. When they launched, each Voyager had about 470 watts of electrical power. Today, they have less than 250 watts, barely enough to power a few light bulbs. NASA has been shutting down instruments one by one to conserve power. The cameras were turned off decades ago. There's nothing to photograph in interstellar space. The tape recorders that stored data were turned off. Various heaters and sensors have been deactivated. By around 2025, there won't be enough power to run any scientific instruments. The Voyagers will still be able to communicate with Earth, but they won't be collecting new data. By around 2030, there won't be enough power for the heaters that keep the fuel lines from freezing. If the fuel freezes, the spacecraft won't be able to orient their antennas toward Earth. By around 2036, there probably won't be enough power to transmit at all. The Voyagers will go silent. The last signal from Voyager 1 will travel at the speed of light across 160 astronomical units, about 24 billion kilometers. It will take approximately 22 hours to reach Earth. Some radio astronomer somewhere will receive that final transmission, a whisper from the edge of interstellar space, the last word from humanity's most distant emissary. And then, silence. The Voyagers will continue traveling for millions of years. They'll carry the golden records through the galaxy, past countless stars, through endless darkness. But no one on Earth will ever hear from them again. Sometime around 40,000 CE, assuming human civilization still exists, Voyager 1 will pass within 1.6 light-years of the star Gliese 445. It won't stop. It won't slow down. It won't enter orbit. It will just sail past, a frozen relic tumbling through space. By then, Gliese 445 will have moved closer to the Sun due to its proper motion. The star that's now 17.6 light-years away will be only about 3.5 light-years distant, closer than Proxima Centauri is today. But Voyager won't know. Its instruments will have been dead for 38,000 years. It will be a ghost ship, carrying messages that no one will ever read. Around 296,000 CE, Voyager 2 will pass within 4.3 light-years of Sirius, the brightest star in our night sky. Again, it will just pass by. No stopping, no contact, no purpose. The Voyagers will continue drifting for billions of years, long after the Sun has expanded into a red giant and consumed the Earth, long after the Milky Way has merged with Andromeda, long after most of the stars in the universe have burned out. They'll be among the longest-lasting artifacts of human civilization. And they'll never reach their implied destination. They'll never be found. They'll never deliver their message. But they carry something precious anyway. They carry the fact that we tried. We are Voyagers, all of us. Not going anywhere, maybe, but reaching nonetheless. Always reaching. Toward the stars we'll never touch. One final thought. In 1990, when Voyager 1 took the pale blue dot photo, it was about 6 billion kilometers from Earth. That seemed impossibly far at the time. The most distant photograph ever taken of our planet. Today, Voyager 1 is about 24 billion kilometers away, 4 times farther. And it's still barely outside our solar system. The nearest star is 40 trillion kilometers away, about 1,700 times farther than Voyager has traveled in nearly 50 years. If someone were watching us from Proxima Centauri, the Voyager probes would be invisible. Not just hard to see, completely undetectable. 2 tiny specks of metal, each about the size of a small car, moving through a void that spans trillions of kilometers. We think of the Voyagers as bold explorers venturing into the unknown. And they are, from our perspective. But from the perspective of the universe, they've barely left home. They're like ants that have crawled to the edge of their anthill, looked out at the vast desert beyond, and crawled back to report that the world is very large. The universe doesn't care about our ambitions. It doesn't adjust its dimensions to accommodate our desires. It simply is what it is, vast beyond comprehension, indifferent to our existence, operating on timescales and distance scales that make human concerns seem quaint. But here's the thing about ants. They're still remarkable. They've built complex societies. They've developed sophisticated communication systems. They've survived for 100 million years. And they never needed to cross deserts to do it. Maybe that's the lesson. Maybe the measure of a species isn't how far it can travel, but what it can build where it is. We have a planet full of wonders, a solar system full of possibilities, a universe full of mysteries we can study, even if we can't visit. The Voyagers taught us the size of the cosmos. Maybe the next step is learning to accept that size, not as a challenge to overcome, but as a context to appreciate. We're small. The universe is big. And that's okay. In fact, that's kind of beautiful. A tiny species on a tiny world, in a tiny corner of a vast cosmos, reaching up towards stars it will never touch, and finding meaning in the reaching. That's us. That's humanity. That's the Voyager message, whether we intended it or not. Not, we're coming to join you among the stars, but we were here, we wondered, and we tried. Maybe that's enough. Maybe that's everything. See you in the next one.